Hello. In this video, we are going to go over an example where we find the equivalent resistance of this combination of 5 resistors, where each of the resistors has a value of 1 ohm. When I'm doing these types of problems, I start by only looking to combine 2 resistors at a time. If you start by trying to combine them all in one step, you will be heading towards disaster. If I'm looking at this circuit, let me start with R1 and R2. Notice that where those 2 resistors meet, that the current can divide along 2 possible paths. Some current's going to go to R1 and the rest is going to go to R2. This is an indication that R1 and R2 are connected in parallel. So let's start by combining these two. I am going to combine R1 and R2 into an equivalent resistance that I will call RA. So what I've done here is I've replaced R1 and R2 with RA. Since they are connected in parallel, I'll combine them using the mathematics of combining parallel resistors. We know that RA is going to be equal to 1 over R1 plus 1 over R2, and we take that result and take it to the power of -1. So R1 and R2 are both 1 ohm. So 1 over 1 plus 1 over 1 is going to give us 2. Then taking 2 to the power of -1 is going to give me 1/2, or 0.5 ohms. So RA is going to be 0.5 ohms. We've now reduced our circuit to look like this. Looking at this quote-unquote new circuit, you can see that the resistors R3 and RA are connected one right after the other, so that if there is a current that goes through R3, then that same current has no choice but to go through RA. This means that R3 and RA are connected in series. My next step will be to take these two and combine them in series. They will combine into an equivalent resistance that I will label as RB. Since RB is a series combination, then to find it, I just have to directly add RA to R3, which is going to be 0.5 ohms plus 1.0 ohm to give us a result of 1.5 ohms. So RB is 1.5 ohms. And we just keep repeating steps of combining resistors 2 at a time. Eventually, we'll just get down to that one final equivalent resistor. For instance, you'll probably see here that RB and R4 are in parallel. I'm going to replace those two with a new resistor called RC. Since it is a parallel combination, RC is going to be 1 over RB plus 1 over R4, and then you take that result to the power of -1, and to use values, we get 1 over 1.5 plus 1 over 1. Then taking the inverse of that, in other words, to the power of -1, we end up with a result of RC is going to be 0.6 ohms. So we've replaced RB and R4 with an equivalent resistance, RC, that has a value of 0.6 ohms. Now we are left with 2 resistors, RC and R5. I think you can see that they are connected in series. So in series, we're just going to add RC plus R5, or add 0.6 ohms plus 1 ohm to get 1.6 ohms. The overall equivalent resistance is now Req is equal to 1.6 ohms. That's the equivalent resistance of the circuit. I'm just going to scroll up here to the beginning of the problem and put in 1.6 ohms for Req. I'm just going to run through it again and quickly summarize what we did. Just to emphasize the point, please note that I didn't even attempt to do it in one step. If I had tried to, it probably would have got way too confusing and I would have ended up doing something wrong. So first I noticed R1 and R2 were in parallel. I combined those two and found an equivalent resistance I just labeled as RA. Then, in this new diagram, RA and R3 are in series, so I just added those two together to create a new equivalent resistance I called RB. I then saw RB and R4 were in parallel, so I replaced them with an equivalent resistance, RC. And finally, we found that RC and R5 are in series, and then I could just add them together to get the final equivalent resistance that I called REQ. And that's how you do it. So to finish off, when we had our original circuit of 5 1-ohm resistors, we found that REQ, the equivalent resistance, was equal to 1.6 ohms. Thank you for watching, and have a great day.